Okay, I want to start the lecture today by talking about networks. Okay, and by networks, we already gave informally the definition. That is, so the collection, okay, or system of pipes, flow lines, and pipelines, okay, that take production from the wellhead, typically from the wells, to the processing facilities. And we not always have networks, okay? So in many cases, we simply have wells that they go straight, each one of them go to the separator. Like in the US, you have gas wells or oil wells that they have their own separator. And that we call standalone wells. Standalone. Okay, that's very typical in the US. You have a lot of wells and each one of them has its own separator. Or you can have also the case where you have wells that go to a common manifold, okay? But then that manifold is very close to the separator, okay? Therefore, you don't have that, that effect. So here essentially it's like each well has the same manifold or wellhead pressure, okay? But so networks, how do they look like? You have it in many cases. I think Songo Songo has a network. The images are here. Okay, you have here a field that is in Russia called Salim. Okay, and I'm not sure if you can see very well from the picture, but you see that you have wells. Wells are these points, and the processing facilities are someplace down here. Okay, so you have one flow line that takes, or many flow lines that take it to a central collection pipe. Okay, and then that central collection pipe is taking it further to the processing facilities, and in the way is getting contribution from different wells. Okay, let me see, I think I have a few more. So that's a field in Russia. It's especially important for subsea systems, okay? Because there you, like I said, it's very expensive to have one line separate for each well, okay? So you commingle the production in one pipe and then that pipe goes to the surface. So that is a network. So it is very typical for subsea systems. Okay. We will see tomorrow that, not only it's only subsea, okay? So, we can have offshore, but with wells that are on the platform. And in that case, you really have like that case, okay? If you have, let me make a short comment here, but if you have your platform like that, and then you have your wells that they are drilled from the platform and go down, okay? Essentially, you have here this case, okay? They're very close to the separator. So in that case, you don't really have a network, but you actually have just like standalone wells, okay? While in this case, you have wells and you have a collecting pipe very long. So in that case, you have a gathering or commingling network, okay? Collection, they call it sometimes gathering system, or sometimes also the name use commingling system. Okay, when I commingle, put streams together of hydrocarbons. Yeah, so let's see, I have one more. That's from a field in Brazil. And there the main thing is that there is some place, there is the export point. It's some place, I think it's either here or here. And you have wells spread all over the Amazonas. Okay, they are drilled in the jungle actually. Okay, so these wells, you have flow lines again that they go and they transport the crude all the way to the port. That I think is this one. Okay, that's Uruku. That's another picture. Okay, so it can be that some cases we cannot use just on a single well basis. We have to start looking at the whole system. How will the collection of wells will perform? Okay, we know how to do it now for one well, or if we can assume that all wells are identical, but we want to know now how to do it when wells might be different. So for that, I suggest we use a thinking experiment. We're going to use a system just with two wells. Okay, we have two wells, then you have that they go to a common point, and then you have a long flow line that ends up on a separator. Okay, so let's call that well 1 and well 2. Okay, so to analyze that system, and we are trying to use the tools that we have learned before. Okay, this flow equilibrium concept. Flow equilibrium, what was the first step? You're having nightmares with the steps of flow equilibrium. You choose a point, right, of interest. So in this case, I suggest we choose the point where everything comes together, okay? Let's do it, let's make it here. Okay, for networks, it's very important where you make your point. Okay, for single well system, you can choose it wherever you want. But for networks, it's very important the selection of the point. So let's make it here. Okay, that's my equilibrium point. And now let's divide and conquer the system. Okay, let's separate. We are going to take one system, this system. Then we are going to have this system and this system here. Okay, we're going to have three different systems. Let's put it numbers 1, 2, and 3. So if and you have one unique point here, that let me call that PJ, okay, pressure at the junction. That is what we call a junction. So I'm going to show first, looking at system 1 only, looking at 1. So how PJ looks like, okay, versus the rate of the system 1. Okay, the rate of 1 is this rate that I have here. How will that curve look like? Okay, going down is available, right? Because I go from the reservoir to the bottom hole to the wellhead to the junction. Okay, so that curve should look actually, we're not sure, okay, how to calculate, but we think it will be something like that. Okay, because I'm calculating the available pressure at the junction seen from system 1, seen from well 1. Now let's do the same for the system 2. How will it look like? If I look again, the same pressure, exactly the same pressure at Q2. Okay, and Q2 is the rate that I have here, Q2. it will look exactly the same, right? It won't be identical. It depends on the IPR of this well and on the tubing length and tubing size and on the flow line. So they won't be identical, but they will have exactly the same shape. There will be an available pressure at the junction seen from system 2. Now, let's go to the last part, which is the flow line, okay? And how will, let's call it 3, okay? How will the pressure at the junction, how it will look like? How will it look like? And here, what Q do I use? It will be Q of the flow line, which is Q1 plus Q2, right? Is that Q of the flow line. How is that curve going to look like? Okay, going up is the required pressure at the junction. But all of these pressures, they have to be the same, right? When seen from one side or the other. So when I put that system together, all of them should reach just a common pressure, okay? And in the case of a single system, if I have two parts, it's very simple to make the intersection with the same rate, right? But here we have that they have different rates. All of them have different rates. This one has Q1, this one has Q2, and this one has the sum of both. So how to solve this problem? I suggest you can use any other approach, okay? But I think for me it's easier to say like an iterative process, okay? I'm going to assume a PJ, okay? That is the first step in solving process. Okay, so I'm going to assume PJ, okay? I'm going to come here to each one of these graphs, and I'm going to knock it and find Q1 star, okay? PJ star, Q1 star, PJ star, Q2 star, and I'm going to make one more, which will be PJ star, and read here QF star. Okay, so I come and in curve 1, read Q1 star. In curve 2, I have to read Q2 star. And then in curve 3, I have to read QF star. Okay. And what now? What is the next step? Is how do I verify that that PJ that I assume is the real PJ? What is the next step? Well, I know we have neglecting something so far. We know at the junction, right, the Q that come in have to be equal to the Q that comes out. Yes, we make a mass balance on that node. There is no accumulation. I have no transient phenomena, no accumulation on emptying process. Therefore, QF equal to Q1 plus Q2, right? Therefore, I come here and I verify that QF star is equal to Q1 plus Q2. Okay, if yes, that is the solution. Okay, I have reached a solution. If not, what do? I again assume another PJ. Okay, and I repeat the process until they are the same. That clear? Yeah. We will see now. That's just a simple, but why? Always that we have networks, we have to do an iterative process. Okay, we have to. We are going to see now mathematically a more kind of formal way to solve it. But graphically, I think it helps if you look at it that way. You have to satisfy, you have one additional equation, depending how many junctions you have, that is going to help you to solve the problem. Okay? So now let's make an exercise. And this exercise was actually in the exam last year. Okay, so I gave it to you yesterday. So it's called network graphical exercise. Okay, and it's exactly similar to what we were doing before. You have two wells, a manifold, a pipeline, and a separator. Okay, the wellheads are very close, therefore I don't have any flow line here. Okay, and the chokes are open. We don't care about the chokes. Okay, and we got the curves for well 1, well 2, and the flow line. Okay, and you have to find, the task is to find equilibrium. Okay, you have to find, if you put the system together, what is the equilibrium rate. Okay, so let's copy that, and you can do it on your, yeah, I can show you how. I like to do it in PowerPoint. Okay, let's see if you can do the same. Okay, so that is the system, and then I suggest you copy this chart, okay, and you copy it to PowerPoint. Okay, so you can do it. You can do it at the same time that I am. Okay, so what was the first step to solve this problem? Assume pressure. Okay, what pressure do we assume? Any ideas? Let's take maybe 80, okay? Let's see if 80 is a good number. So we go here to shapes, and we take a line, and we draw just a horizontal line on 80. Okay, I can maybe change the format, make it simply thicker, make it red first, and then make it thicker. Where is the thickness? Oh, here, weight, 3 points. Okay. 80 goes here, knocks and goes down, and then I have to make another line. I can copy this one. Okay, in the exam I think you were doing it by hand, so okay, and I got a rate of how much is Q1 star is 8.2, 0.4, 0.6, 0.8, 8.8 e to the 5. No, sorry. Point, that is 4, 8, 9.2. I think the division here is by every 4, right? I think. 0.4, 0.8, 9.2, 9.6, yeah, so it's 9.6. 9.6. I'm going to copy that, paste it in my notes here. Wait. Okay, and then I here say I assume PJ star equal to 80, okay, bar, the junction, and then Q1 will be 9.6 e to the 5 standard cubic meter per day. Okay, now we go to the second well, then I make another PowerPoint Okay, I want to keep the lines here. So let's go and copy this chart. Okay, I'm going to send it back. And what pressure? The same pressure, right? The same 80 that I assumed before. So I have 80. Okay, goes back. And then I go and knock it down. What will be the rate? Okay, I think here we go 1.1, 2, 3, 4, and 5. Okay, so it's 1.1, 1.1, maybe 7. Okay, 1.17 million from that plot. Okay, so here with PJ 80, then Q2 was 1.17 e to the 6 standard cubic meter per day. And then we go the last step. Let's call this iteration 1, okay? Because we know we have to make different iterations. Iteration 1, okay? So now we go on the last one. So we copy this one. Okay, and you see here that pressure is actually quite high, 80. It's almost on the edge of the plot. So I start to suspect the intersection won't be here. But let's do it anyhow because we already selected 80. And we are finding that, okay, if we make some extrapolation of that curve, we find that we have 1, 2, 3, 4, 5, 3.3 e to the 6, okay, on this curve. So our assumption was too high, right? The pressure was too high, I think. Let's verify now. Okay, PJ will be 80 bar. Therefore, QF was 3.3 e to the 6 standard cubic meter per day. Okay, and then we verify. What was the first rate that we found? 9.6 e to the 5. 9.6 e to the 5. Plus 1.17 e to the 6. Is that equal to 3.3 e to the 6? It's not, right? This is like a million and this is 1.7, so that gives you like 2 million. Okay, and you should have 3.3 million. It's not. Okay, so what is the conclusion? We have more flow in the flow line than what you have from the wells. Okay, how do you get more flow from the wells? If you lower the pressure, right? If you see at this chart, we need to increase this number. Okay, to get that number to the right, we have to lower. We have to try a lower pressure. Okay, what number should we try now? Huh? 40? Okay, let's try with 40. Second iteration, okay? Okay, we try with Pj equals 40 bar. And we go back, we can use the same sheet that we have already. 40 is all the way down here. Okay, how much is that? 40, that gives me 1.2, and that's 1.4. So that's 1.3, so that's so that's 1.25, okay? 1.25 million. So let me copy that once more. $1.25 okay, with PJ 40 bar, I have QG, that will be 1, right, of 1.25 million. Now let's go for well 2. We're going to see very soon how do you solve it numerically, okay? But graphically, I think if you have no computer, like in the exam, that makes your life easy to solve, and also to learn like the physics of how do you solve the system. Okay, 40, and then that will be 1.5, 6, 7, 8, 9. So 1.5, 6, 7 maybe. Okay, 1.67. Let me copy that. Q2 will be 1.67 million. Yeah, now we go to the next curve, the last curve, which was a pipeline, and we go with 40, and that's giving me 1. This is 25, 25, so a bit 1.2, okay, 1.2 million. Okay, Q of the flow line was 1.2 million. Therefore, I go back and check, okay, how much was Q1 plus Q2, is it equal to QF? Okay, we have 1.25 e to the 6 plus the other number was 1.67 e to the 6. And we have on this side 1.2 e to the 6. Okay, how much is that? That doesn't work, right? We have now more on that side and less on that side. Please note that the effect is the opposite. Here, if I lower pressure, I'm going to get more rate, okay? But on the curve of the pipeline, if I lower the pressure, I'm going to get less rate. And that's simply how it works. If I, on this system, going back, right? On this system, if I lower this pressure and make it lower and lower, the fluid can flow easily from the formation to that point. It's like lowering separator pressure. But on this system, If I lower the pressure at the inlet, then I can flow less flow, okay, because I'm flowing against a constant pressure boundary. What is the next guess? Okay, I suggest, to make it a bit smarter, we create an error, okay? A factor called an error. That will be QF minus Q1 minus Q2, okay? That equation. So how much was the error here in the first point, in the first iteration? So let's calculate that. 3.3 e to the 6. Okay, so let's see, 3.3 e to the 6 minus 9.6 e to the 5 minus 1.17 e to the 6. Okay, so that gave me 1.17. Okay, that gave me exactly the error, gave me something positive, okay, 1.17 e to the 6. Okay, that's the error. Now let's calculate, that's the error of iteration 1. Now let's calculate the error of iteration 2. Okay, let's see how much is that. And here we have the same, 1.2 e to the 6 minus 1.25 e to the 6 minus 1.67 e to the 6. And now in that case, I get a negative number, okay, of the error. The error of 2 okay, the error of 2 is minus 1.72 e to the 6. Okay. So if you were plotting this, this is like a solution of an equation, okay? If you're plotting the error, right, versus the pressure at the junction that you are assuming, okay? Initially, if you had 80, right, you are getting a positive number, 1.7, 1.17 million, okay? But if now you're putting 40, let me make that a bit bigger, okay? If this is 40 now, you're going to get a negative number, okay? 1.72 minus 172 million, okay? So what I will say, the solution is someplace in between, okay? Because in between is changing sign. Here is positive there, here is negative there, so it should be someplace in between. So I say to find the next seed, I will say, why not we make a straight line, okay, between these 2 points? And then I find exactly where it's going to become 0, okay? So let's see if that works. How do I make that intersection? How do I find this point X? Okay, we can do it. First we calculate the slope of this curve, right? What is the slope of that curve? Is, remember, y2 minus y1 divided by x2 minus x1. That's the slope m, okay, of that curve. And what is y2? Y2 is 1.17 e to the 6, okay, minus y1 is minus 1.72 e to the 6, okay, and then divided by 80 minus 40, and then here I obtain my slope. How much is that? You're letting me do all the work. 1.17 plus 1.72, right, divided by, we have to divide by 40. Okay, so we have 0.07225 e to the 6. Okay, that's the slope. But now we say that the slope of this new point should be the same. If I make it from here to here, okay, I should have exactly the same slope. So I say m can also be, let's use y2, okay, y2 minus y, which will be this point here, okay, divided by x2 minus x, that is 1.17 e to the 6 minus, what is the value of the error in this point? 0, okay? So simply we put 0, divided by x2 is 80 minus x that we don't know where it's going to be. That's the next point we're going to guess. And that will be equal to 0.07225 e to the 6. Okay? Now I clear x. How do I clear x? I put it up, then I bring this guy down. 1.17 e to the 6 divided by 0.07225 e to the 6. And then I say this one will be minus 80x. Is that correct? I hope so. You are the ones making the quality control, okay? I'm the engineer and you are the bosses, you are the jefe. Okay, so how much is that? E to the 6 goes away. 1.17 divided by that. How much is that? 1.17 divided by 0.07225. Okay, and then I have 80 minus that. Okay, 63.8. So I get that x, according to this interpolation, it should be in 63.8 bar. Okay, and remember, this function is probably not linear. Okay, so we're making an approximation. Probably the function, it does, is something like non-linear, like that. But we don't have anything else in between, so we make the assumption is linear. But let's try with 64 bar, okay, for our third iteration. The third iteration, iteration 3, okay, with PJ 64 bar. Okay, so let's see 64. Where is 64? That's, I think that is 64 actually. Okay, because each one of these are 4, 8, 72, 76, and then 80. Yes. So that is 1.1 actually, okay? 1.1 e to the 6 for Q1. Let's copy it here. Okay, Q1 is 1.1 e to the 6. Okay, now let's calculate Q2. We have to go to 64. 64 will be, again, we have here in, I think it's the same, yeah. 4, and then this guy here, how much is that? 1.4, okay, e to the 6. Q2 will be 1.4 e to the 6. Now let's calculate QF, and we have to go here to 64, and 64 is here. Okay, we have 2.55, okay, more or less, so 2.50 something, okay, 2.55. 2.55. Okay, QF will be 2.55 e to the 6. Okay, therefore we check how much was Q1, 1.1 I think, 1.1 e to the 6, plus Q2 was 1.4 e to the 6, and QF is 2.55 e to the 6. You're still not, so here I have 2.5 and here I have 2.55. Close enough, okay? For our purpose, to make it graphically, that is the solution. The solution is P at the junction is Q F equal 2.55. Okay? Understood? Yeah? So now, let's do something else, something different. Let's say so this mode was to say that the choke was fully open, right? Here we're making our calculation assuming the choke is fully open. Now, let's say that I came now to the reservoir engineer, okay? I made my calculations, and then I say, well, well 1 will produce 1.1, and well 2 will produce 1.4. Reservoir engineers goes in panic, okay? They say, no, if you produce those rates, we're going to get too much sand production from the well. The formation will collapse, and then it will start producing too much sand. We cannot accept those rates, okay? He said that the acceptable rates that we should have are Q1 equal to 8 e to the 5, okay, according to reservoir engineer. Okay, the Q1 should be less, okay, should be less than that. Okay, you have to limit it. And the Q2 also has to be less than 1, okay, e to the 6. And he's asking, is it possible to produce those rates? What do you think? Well, the rates are less than the equilibrium rate, right? If I have no choke, everything is open, I get a high rate, okay? And I have to reduce it. And so in that case, it seems that it's possible. It like logically, it gives you the idea, it should be possible, okay? But how do I verify it? You remember, what have we done when we had a single system, okay? If we have a single well system, okay, and we were plotting wellhead pressure, okay, Q PWH was something like that, and then this one was the P into the flow line. This is the value we will flow if, we put two things together, no choke. But now reservoir engineer told me I have to produce this value, right? This Q, desired, for some reason. So what did we have to do there? We came into the available curve, right, with that rate. We read the P available, Okay, and then we came with the Q to the required curve and we read the P required, right? And then we say this one is greater than this one. Therefore, it is possible, and I have to put a choke in between to bring down the energy. That's what we have done, right? Yes? So let's try to do the same here in this example. Okay, we have the curves, so we can try and calculate if the available is greater than the required. Okay, so let's go back to the rates he wants is 8 and 1 million. Okay, that's the rates the reservoir engineer wants. Okay, so let's go back. 8 is here. Okay, for well 1. Let's extend it all the way up. That gives me a pressure of 96. I think that's 96. Or 8.4, 0.8, 9.2, 9.6. Okay, 96 bar. So let's say here P available. Okay, P wellhead. I should call it P wellhead available for well 1 is equal to 96. Okay, that's the energy I have available if the well is producing 8. Okay. Okay. Now let's go to well 2. If I'm producing, what was the rate the engineer wanted? 1. Okay, so I go here and I cross it to the left. How much is that? It's like 90, right? So I select. They come too big, these figures, I don't know why. We have to complain with Bill Gates. Okay, PWH available of 2 will be 90 bar, around 90 bar. Okay, and now I go and I calculate the required. Okay, from the curve. What is the required? How much is the rate I want to flow? It will be 1.8, right? Because it's 8 plus 1 million. Okay, so this is 1.5, 6, 7, 8 will be here, and the pressure will be there, 50 bar. Okay, on the flow line. Okay, so here P required, okay, P with solid P in, okay, of the flow line will be 50 bar. So is it possible to produce this rate? These rates that the reservoir engineer wanted. Let's go one by one, okay? What was the P wellhead available for well 1? 95, right? 90 or 96, okay? 96. Then P wellhead 2 available was going to be 90, and the P in required of the flow line is going to be 50. Therefore, PWH1 is greater than the required, okay, than in, and P wellhead 2 is also greater than the required, okay. Therefore, I have enough energy available, therefore the rates are feasible. Okay, I can produce those rates. Okay, however, what do I have to do? I have to bring the energy down. Okay, how do I do it? With a choke. Okay, what's going to be the delta P choke for well 1? Okay, it's going to be 96 minus 50, that is 46, and delta P of choke 2 will be 90 minus 50, that will be 40 bar. Okay, you see, two different types of calculation and very different in the computational requirement. The first one, we were doing equilibrium, okay? No choke, simply put together and see how it works. And it took a lot of time. You see, it took 3 iterations at least. We have to make 2 and we have to make a trick to try to approximate the solution, okay? If the rates are below that, the equilibrium point, okay, you can simply fix a rate and then calculate the choke. Just 1 iteration, that's all, okay? Okay, I think that was a question on the exam last year. But now, so I want to, now let's make it, usually we have to solve it on the computer, okay? To create a plot when we get especially big networks, we have to find a way to solve it on the computer. So let's look at, first let's look at how many equations we have, okay, and how many variables we have. Okay, and let's go system by system, or element by element. Okay, so let's go on first on the well 1. How many equations we have for well 1? We have the IPR, right? That was QG CR PWR squared minus PWF squared to the power of n. Okay, here how many unknowns we have? We don't know this pressure and we don't know the rate. Okay, so we have, let's put it here, unknowns, and here we have equations. How many equations we have? Okay, here we have 2 unknowns, 1 equation. We have to continue, we have to find until these 2 are the same. So well 1, we also have the it was QG CT, right? PWF over ES squared minus PWH squared to the power of 0.5. How many unknowns we have there? We have the rate, but it was the same unknown as before, right? But we have this guy here and this guy here. So we have 1 additional unknown, okay, and 1 additional equation. Yes, the additional unknown is PWH, but we have 1 more equation. So far we have 3 and we have 2. Okay. Now we go to well 2. What do we have in well 2? Exactly the same 2 equations, right? But now with the conditions, this was 1. Now with the conditions of 2, QG2, CR2, PR2 squared minus PWF2 squared to the power of n, 2. That was n1. Okay. So here I have, this one is an unknown, this one I have, this one I have, and this one is also an unknown. Okay, so I have 2 unknowns and 1 equation. Let's go now to the tubing equation. QG2 CT2 PWF2 okay, that is 1 more equation, right? And how many new unknowns? Just 1. Okay, so here we have just 1. Okay, so here we have so far 4, and here we have 6. Okay, it's not looking good. Now let's see the pipeline, okay, the flow line. Okay, the flow line, what was the equation of the flow line? QG1 plus QG2 was going to be equal to C flow line P in squared minus P separator squared to the power of 0.5. Okay? What unknowns do I have here? This one, but I had this one from before. Okay, I had it here. This one, but I had this one from before. I had it here. And now this one. Okay, so I have one more equation, but I have one more unknown. I'm catching up. Here I have 5 on this side, and here I have 7. Okay, so I need one more equation. What is the equation that I'm missing? What did we use in the graphical solution to close the system? The mass balance, right? At the junction. So if we make, that's the key mass balance. A mass balance says that QF is Q1 plus Q2. Okay, so here we have one more equation. Okay, and this is exactly QF. Okay, and we have 0 new unknowns. Okay, therefore, if we make the sum up to see if it's consistent, we have 1, 2, 3, 4, 5, 6. Okay, and no, we have one more here. 1, 2, 3, 4, 5, 6. 1, 2, we still have 7. We made a mistake someplace. We're missing one. What equation are we missing? Two, one. Oh yeah, of course, we are missing one more equation. Sorry, that's not the total number of equations. What equation are we missing here? Something very important, right? That P in, okay, is equal to P wellhead 1, okay? And then you have that P in is equal to P wellhead 2, okay? So here we have one more equation. Yep, and here basically, let me make it like that. Let me make this Q of the flow line, okay? Yeah, I know what happened. Q of the flow line, so that will be 2 unknowns instead of 1, because I have Q of the flow line. Okay, here I have 0 and 1, and here I have 0 and 1 and 0 and 1. So there, now it should be consistent. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 equations and 8 unknowns. Okay, this system can be solved. Okay, it's a system of equations that is consistent and I can solve it. Okay, so let's do it. Okay, we have another exercise, and that's the way actually we solve networks using Excel or using any other tool. Okay, we don't solve it graphically unless it's very, very simple. But I suggest we do it in Excel just to solve it the way we will solve it normally. Okay, so it's exercise 5, gas network. And I'm not sure, I don't think it's the same system that we had before. Okay. I'm not sure if that's who has the memory stick? You have, because I'm going to give you another exercise, not this one. I don't like too much this one. I copied the wrong one. Sorry. Yeah, it's this one. Okay. Okay, so let's use this one. Okay, just use this file. It's called network gas wells. It's not the one that we had before. We just click here. Okay, downhole networks. Now we are going to go to a topic called reserve estimation. Okay, reserve estimation has two main purposes. One of them is to estimate N or G, okay, which we call in original oil in place or original gas in place, okay? But we are using SP nomenclature, so we're trying to use just one letter, N or G. And we also want to estimate the NPU or the GPU, the ultimate cumulative production of gas or oil. And this is known as TRR. It's called total recoverable reserves. Okay? And that we try to do everywhere since we have the discovery and the appraisal. We try to find the volumes we have, okay? So before DG0 all the way to DG3. We try to see more or less what kind of volumes we have, okay? And here, just to show you an example, I'm going to share that, maybe put it on a memory stick. It's available, you know, freely on the web. The Canadian government, they release some of the, you know, remember at the end of DG3, okay, here we were identifying a business case, exploring, trying to find, you know, if we have oil, try to make drilling, trying to define the size. Then DG0 to DG1 and a bit inside DG2, we're trying to find a feasible concept, okay, how are we going to develop our field. DG2 to DG1 to DG2, we're trying to select a concept, the best concept, and then we're trying to expand that concept, okay? And DG2 to DG3, we have to make all the details, okay? How do we develop the field? And that after that process, DG3, we issue a PDO, a plan for development and operations, that gives like a cookbook. How are we going to develop our field? Okay, so here I have one. If you're curious, you can go and read what it has. Okay, that's for a field called Hebron in Canada, offshore Canada. And you see all the different parts it has. It has explanation about the area, the history, the scope, alternatives, okay, how are we going to develop it? So FPSO, gravity-based structure, we're going to discuss about that tomorrow. The facilities, what are we going to use? So let me just maybe scroll through the report, okay? It's a report, 500 pages, okay? And that's only the technical part. On top of that, you have one which is the environmental consequences, typically. That's another 600 pages. So and someone has to read it, right? The government has to read to make sure that they're making the homework. So that's what you're preparing basically from DG2 to DG3. All making that report, okay? So that's the overview, where is it located, okay? What kind of block is it? How are the reservoirs located? Then you have the schedule. Then how are we going to produce it? Okay. Is it this one or this approach or this approach? What kind of approach were considered? How that's to see which approach is better. Okay. They have different criteria: economic, technical, environmental. Okay. So then they explain a bit how, where they're going to put the things. We're going to talk about that tomorrow. Okay, the subsea system. Okay, then comes, you see they even have different font type. Okay, so that was done by the geologist and that was done by someone else. Okay, and they forgot to put the same font, so someone got fired, but Okay, so they explain about how the reservoir was formed, the geological structure, that we don't talk too much in this course. Okay, then that's when it was generated, all the oil and the gas. Okay, from which year, million years, 150 million years it started generated, and then most of the oil was generated that time. That's geology, poetry. Okay, then we come to something more interesting, that taking some scores to see how they are, and we are just page 100. Okay, I'm going to go forward a bit quicker. Okay, that's the hydrocarbon, what kind of hydrocarbons you have. Okay, that's a gas chromatograph, saying that's the carbon number. Gas chromatograph, okay, so that tells you the carbon number, and that tells you the amount of how many components you have. Okay, so here you see you have some peaks, C30, here you have some more peaks, okay, C10, C15, that's our oil samples probably. Okay, then you come the people with seismic, they try to find out, you remember I told you that maybe I didn't tell you, okay? In exploration, they send, I think I have some pictures here. Okay, I think they are here. No, they're not here. Okay, they are for sure, they are here. Okay, that's the phase that we call pre-exploration. No, it's here. Okay, but I don't think we discussed that part yet. That was going to be maybe tomorrow. Okay, but they, sure where I took that from, okay, but that's in exploration, okay, it's exploration seismic. Okay, they use an offshore. Here we're talking about offshore. Okay, the basic idea is that you send a wave down. Okay, you make a wave, and that's typically with an explosion. Okay, here we call an air gun. You send the wave down. The wave travels very fast. Okay, and then it will start to reflect in different, where you have a change of properties. So here in the sea, everything is more or less uniform, but here you have a change and it will reflect, okay? And that's the first one that reflects, that comes up. Then you have entering to another layer with different properties. It reflects, and then you get a different, you get reflection here. So on this cable, what you have are like microphones, okay? They are called hydrophones. So they pick up the signals of the reflection, and they try to make some sort of a map of what you have below the surface. Okay, and that map, the whole story was to show you that that map is exactly what you have here in this Hebron PDO, okay? Try to map the different things, and this requires a lot of power, okay? Computing power, because you see there, this boat is just going, is flowing, going on one direction to map a lot of things. So you have to go process the image and try to make the map very quickly, process the data, okay? And then you end up with something like that, okay? And then from there you try to see where are the layers, where are the faults, and where I might have hydrocarbons, okay? Just trying to, that's the job of the geophysicist. Okay, let me copy that so you have it in the notes. So after you do that, you do a lot of processing, you do a lot of sweating, then you end up with this image. And from the image, you try to find the volumes, you try to find where you might have something, where do you want to drill, all kind of things. Okay, it's very useful. You try to get like a X-ray of the formation, okay, from here to here. It's not so simple. You have to do a lot of things, a lot of assumptions, but you know, that's what we try to make. So that's the job of the geophysicist. Okay, we can also do it in land. Okay, let me see, in land there is a nice figure here. Okay, you do exactly the same. You have a place where you create an explosion, okay, and then you put a lot of microphones that you deploy, and then they are measuring the reflection. Okay, you don't have the water layer and you cannot do it, so you have to go deploy all of this setup and then measure for a time, then take it out, put it in another place, and go and do the same. Okay, so it's more time consuming. Okay, that's when you do it on land. Okay, so that's land-based seismic. Okay, but let's go back to the PDO. Okay, let's maybe rotate back. I think we have to rotate like that. Okay, that's the different structure where you are. Okay, time to depth. Okay, here, this conversion, what they're saying here is exactly time to depth. Okay, they get some time when the wave is reflected, and then from there they have to convert when is that reflection happening. Okay, so for that they have to make an assumption of the velocity of the wave. Okay, how quick is the wave traveling? Okay, depending on the layer, they will travel at different velocities. Okay, and they will reflect, you will get the reflection at different times. Okay, again the same thing, discussing that there are all kind of things. Then you try to map the properties. Okay, hydrocarbon pore volume, we are going to see now what it is. They try to get porosity. Okay, finally we have references, comes petrophysics. Okay, and we are going to talk about that also later today, just now in a second. Okay, we're going to try to make that distribution, okay? But basically, we have here two things. When we make exploration drilling, okay, let's make it, maybe take it right away, okay? Exploration drilling. Okay. We do two things. We drill our well, okay, in the formation, and we can do two types of analysis. One of them, well, we can make many, okay? But one of them is, instead of drilling with a normal drilling bit, we drill with a bit that has a container, okay? We drill and then we take a core, okay? We take a piece of formation that looks like that, okay? And we retrieve it and we analyze it on the surface. And that's going to give us a lot of information about, for example, porosity, okay? About the fluids, about the saturations, okay? It's going to give us information about permeability. Okay? And that's what they are, I think that's what they are doing here, because they say porosity and they say the samples, okay, using 2,287 core samples from 6 core wells, okay. So they have 6 wells, okay, and they make 2,287 core samples, okay. And finally, of this is called coring, okay, coring. And this is what I have here. This thing is a core sample. Okay, they took all of them and they measured and they obtained, and we're going to, that's exactly the exercise we're going to do here in class. They found what was the porosity of all of these samples, okay? And this is a probability distribution chart. We're going to see how that looks like. Another thing that petrophysics does, the petrophysicist does, is they send on the hole, okay, they send some tools, okay, that they emit some kind of signal, okay. They have different types of instrument, and that's to measure, for example, if we have different layers, okay, typically we have different layers, so they pull out the bead, okay, and they pull out, or they can do it while drilling also, but they pull out the rig and then they send a cable with that instrument, okay, and they start measuring, okay, and you have different layers with different things, okay, so they can first detect what kind of layers you have, okay, if it's something that can have hydrocarbons, or is something that simply is a seal layer, okay? Okay, but also can tell you something about if it has water or not, okay, about the water saturation and detecting hydrocarbon bearing rock, okay. But tell you something also about the water saturation, and also can tell you also where is the contact, okay. You can see, for example, the oil gas contact, okay. If you know that you already have a reservoir, okay, you typically have in a reservoir you have 3 main things, okay. You have gas, then you have oil layer, and then you have a water layer, okay. And you want to know exactly where this is called the oil gas contact. Actually, it's not OGC, it's GOC, gas oil contact. Okay. Then you have this other one, which is the oil water contact. Okay, and you want to see exactly where they are, just to know where to drill your wells, okay. If you want to produce oil, you don't want to put it too close to the gas or too close to the water. You're going to get into these problems that you start getting coning of water or coning of gas. Okay, so those are the maps that the petrophysicists make, okay. Saturation of water, Okay, they collect all kind of data, and they try from there to find out where is the area, where is the producing hydrocarbon layer, and what is the water saturation, where is the contact, and so forth. Okay, so that's petrophysics, that's called logging, okay, exploration logging. Well, let me make it here. So that's called exploration logging. Okay, and you end up with some maps like that, and they show with depth, okay, that's the depth, and they tell you what do you have there. And you have all kind of measurements. They have conductivity, they have gamma, they have all kind of measurements that they make. We are not going to cover them here in class. And from there they try to find other things. Okay, you see they detect something there that you have here, some change, something. Those are the cores, okay, that they collect some pictures of the cores. Here you see fluid contacts, and then they try to determine where is the field oil line, okay, and the depth, that's oil, and then you have the water line. Okay, so they say the contact is more or less here. Okay, and then they made the porosity, try to get once more from the permeability. Okay, and I think that should be okay. Come the reservoir, and that's what we are going to talk about just now. Okay, reservoir, the first part. Okay, here they say, well, all the structures you have, but one of the most important parts. So here you see the composition you have, the type of fluid you have in the formation. But one of the most important things that have to be made here, so that's again properties, properties. It should be coming soon. So that's permeability from the petrophysics. I should be getting close. Reserve estimates, okay? A big chunk of that's what we have to do from DG0 all the way. We have to calculate the original oil in place, and we have to calculate also the total recoverable reserves, okay? And we are going to use exactly the same method they are using, but of course we are going to use a much simpler reservoir, okay? Here they have a very complicated, if you remember the figure they had before. Okay, that's what we have done, yesterday. They have the required curve, okay, the tubing performance for different, so they propose a well, and then they calculate the rates, okay. Okay, that's oil, that's what they get with oil. That's exactly what we have done, I don't think it was yesterday, where we calculate the production profile. So they are getting this profile, okay, of oil, okay. So that's exactly what we have done yesterday. But now, just to show you, it was here, I think, all the way to the top. Okay, they have a very complicated case. We're going to make it for a simplistic case, but we are going to use the same method that they use. Okay, so let's take a case, okay, and let's assume you have, so let's say it's an oil reservoir, okay, is an example, oil reservoir. And we want to calculate the NPU, okay? Or that's the same as the TRR, total recoverable reserve. How much after the field is closed, after everything is done, how much I'm going to recover, okay? What is the oil I'm going to recover? So for that, first I need, okay, I have a, let me say, just to make, it doesn't have to be a square, okay? But let's say that it's something like that. It's a block, okay, that I have. This one has certain volume, okay? Volume of the rock. That's what I call the volume of the rock. If it's squared, this one will be simply A times B times C. If it's like a disk, okay, then it will be P phi squared times 0.25 times H, okay? And you can have all kind of complicated shapes. That number you get it from you know, people that the geologist and the geophysicist, okay? But now oil is not filling all of it, okay? It's just filling. If you take a closer look at that, you will see actually that you have some particles of sand, okay? You have some particles of rock, okay, that are occupied, and only the space in between the pores, okay, is what can be filled by liquid, okay, by fluid. But we also know that the porosity, what is the definition of the porosity? Porosity, phi, okay, is the volume, let's say, of the holes, okay? How many holes do I have? The volume divided by the total volume of the rock, okay? Of these holes, of these cavities, okay? That maybe let's call it cavities. Okay? Therefore, I multiply VR times phi such that it's going to give me simply these cavities, okay? Now let's continue looking further, okay? We are looking big and then starting to go inside, okay? If we look again at, you know, the interpore space, okay, you will see that we don't have normally pure oil. We mentioned earlier that typically we have water, okay, that was there, and that water likes very much, has a very good affinity for wetting the rock, okay? It's just sticking to the rock. And the oil is going to be in between, okay? We are talking about an oil reservoir. Is going to be simply in between. So not all the pore space is filled with oil, just, you know, just part of it. So there is something that is called saturation, okay? And I can have saturation of oil, saturation of water, but the saturation of water is the volume occupied by the water divided by the volume of the cavity. Okay, how much of the cavity is occupied by the water? Okay, and the same thing, you have saturation of oil, saturation of gas, and always saturation of water plus the saturation of oil plus the saturation of gas should give you equal to 1. Always, right? Because you cannot have, if we are talking about the fluid, the space occupied by the fluid, in that space you can only have fluid. You can only have gas or water or oil, nothing else. Okay? Therefore, we come back here to our equation, and what do we multiply it by? This was volume of the cavity, right? Volume of the fluid. And to get the volume of the oil, what do we multiply with? S oil, right? Or we can also multiply S oil is equal to 1 minus S water, right? And this saturation is what we call the connate water saturation. Why do we call it connate? Okay. Is the original. Okay, I haven't done anything, I haven't done any injection, nothing. So the original water that is there in the core is that number. Okay, SW. So now we have here the volume of the oil, right? Almost. There is one thing, if we look now closer at that rock, okay, and that's what the petrophysicist is looking at. If we look at the rock, okay, it's not exactly 100% pure, okay, it has a lot of things in the center. So it has some layers that don't have any hydrocarbon, and actually they might be some sort of a seal, okay, they might be some dirt, some other type of rock where you don't have any hydrocarbon. Okay? So what the petrophysicist does is that he goes with his logging tool and he's trying to map how much of that is. So if you see it on the side, okay, you have one H1, he tries to find those heights, H2, H3, H4, and let's say we have here H5. Okay, we found 6 layers in that rock, okay, in my reservoir. So he defines a new parameter called N net to gross, okay, that represents how much of the vertical height is actually filled by hydrocarbon. Is hydrocarbon bearing rock, okay? And the way he defines it, he simply says is H1 plus H3 plus H5 divided by 1 by the total. Okay? How much is filled with hydrocarbon divided by the total? We know it's going to be dirty, it's not going to be pure, it has some things there in between, so I try to define that number. So therefore, I multiply here by this net to gross, okay, net to G. Net to gross. Okay? To modify that volume that I had of my rock. Okay, so we have there the volume of the oil exactly at those conditions of reservoir pressure and temperature, there in the bottom, okay? Now, what happens when I bring that oil to the surface? Okay, if I have that oil, right, let's say I have a cube of oil, let's use green, okay, oil, we usually use the color green. At PR and TR, and we bring it, okay, when we produce it, we bring it to standard conditions, okay, P standard conditions and T standard conditions. I bring it with a tanker to the market, okay? What's going to happen with that oil? The volume will change, that's one thing, and then the other thing is it's going to release gas, right? Yes? So you have two things. That's very correct. You have oil will be changed, okay? Will change its volume, okay? But also it's going to release gas. And the volumes that you are selling, okay, reserves or TRR or G, everything has to be given in what the amounts that I can sell, okay? It's not very useful to say, okay, it's not very useful to say to the manager, you have so many barrels of oil down, okay? You say, well, how much of that can I sell? Okay, and for that you need, so petroleum engineer, they created a factor called the oil formation volume factor, okay, called BO, that depends on pressure and temperature, okay. And that's simply the way it is defined. If we have here a volume of oil, and here we have this volume of oil at standard conditions, and actually we're going to use, I like to use O with a hat, okay? That means standard conditions, okay? Simply, this BO is a factor that is the volume of oil at a given pressure and temperature divided by volume of oil at standard conditions. So it's simply a ratio, okay? Petroleum engineers, they don't like to, talk about compositional calculation, equation of state. They don't like to talk, so they say it's just a ratio. We make our life easy, okay? A ratio between the two. Let someone else find that number for us, but we like to use this ratio. That number is typically something between maybe 1, okay, and might be all the way to 2, okay? That means, okay, typical numbers maybe 1.2, 1.3, okay? And that means that you have more in the reservoir, and when you flush it up, because it's losing gas, okay, then it's going to shrink, okay, it's going to shrink. If it didn't have any gas, okay, just by the compressibility, it will expand, okay, because the pressure here is higher, and then the pressure up is lower, it will expand, okay? But because of it's losing gas, it's losing mass, that's why this number is around that. So how do I convert the equation I had before, right? Was we're saying N equal to VR times porosity times 1 minus the water saturation times net to gross, right? What else do we need? Okay, that's giving me this number here. That's the volume of oil. Yes? At that pressure and temperature, at that reservoir pressure and reservoir temperature. Okay? To calculate the volume at standard conditions, what do I have to do? Divide by BO. That's correct. And that's one simple equation to calculate initial oil in place. Okay? And if I want to calculate the NPU, the ultimate cumulative production, what do I do? That's the total recoverable reserves. That's exactly the same as before, right? But now I multiply times the recovery factor, FR. That's the recovery factor, okay? Which the recovery factor is defined as NPU divided by N. Okay, simple. That's the equation we're going to use now for our reserve estimation. Okay. So if you put it in a graphical way, you can say that I have here, let's call it in the center, reserve estimation. Okay, where this NPU will be equal to volume of the rock times phi 1 minus saturation times net to gross times FRU divided by BO. Okay, that's that equation. Okay, and the input is using is VR, then it's using phi porosity, then it's using SW, then it's using net to gross, and then it's using FRU, and at the end it's going to give you NPU. Okay, that's the process, that's the equation. You can have something more complicated, you can have inside using a program or having a more complicated geometry or having a sum of different things. For our case, we put it very simple. It's just that equation, okay? If we make that equation, we can find out NPU. Okay, and that can give the company an idea comparing with other projects to see if it's worth investing or not. Okay, if they have the same size that another project that was very profitable, so they say yes, let's go for it. Now, one of the problems is that these numbers that I have here, they are not unique. Okay, you don't have just one number. You have a range. Okay, you have from a minimum all the way to a maximum. Your field won't have a unique number. Why? Because you already saw by doing coring, you might get different porosities. Okay, also different saturation. Net to gross also might be different some places in the field. The volume of the rock also might be very uncertain. Okay, so to do that, so to cope with that, so this let's put here, this calculation is not deterministic. Okay, and deterministic means that you have one input and then you have one output. Okay, it's rather probabilistic. Okay, so I have a range of values and I have to see how to cope with that. So let's, for example, how do we do that? We do a probability distribution function. Okay, or also referred to as PDF. Okay, probability distribution function, where we say that you have, let's talk about the porosity, right? You have phi minimum and phi maximum, but then you have a distribution of which one has the highest chance to appear, okay, or which one is the most likely. In this case, okay, that's the probability. All of them have the same probability of occurrence. Okay, you can have everything, everything can appear. Okay, you can have other probabilities where one value is like has a higher probability. Okay, you can have some other that are maybe something like that. Okay, that are like a normal distribution. So that's something that people can guess. Okay, if you have no idea, you haven't done any measurements, nothing, you simply say, well, I know that it can be between a minimum and a maximum, but I will assume that all of them are the same. I have no information whatsoever. Okay, but if I have measurements, I can build that distribution. Okay, and then I can use that for my analysis. Okay, so let's make an exercise, another exercise. Today is the day of exercises. Okay, so class exercise. And our objective here is to find the PDF of porosity, okay, based on coring measurements. Okay, I made a lot of coring. I think they did 100. I have 100 values there. So I have 100 and I want to calculate how the distribution looks like. Okay, so for that, let's go to the Excel sheet called porosity distribution, number 6. And we're going to do exactly the same. People were doing coring, they were measuring the porosity for each one of these cores, and now I want to see what distribution I have to use for the reserve calculation, reserve estimation. Okay, so you have here measurement 1, 2, 3, 4, 5, all the way to, actually there are 50, okay, measurements of porosity, and you have different numbers here. Okay, so the first thing we do is to define, like what I showed before, you have to define the minimum value of porosity, okay? Porosity minimum, okay, and porosity maximum. Let's create two cells here at the top where we call it porosity minimum and porosity maximum. The units of porosity, in this case, is a fraction, so it doesn't have any units. It's a ratio between two numbers with the same unit. Okay? How do I find the minimum of that column? Okay, I want to find the minimum number here. How do I do it? Okay, I say minimum, I call a function called minimum, and then I select the whole column. Okay, and it tells me the minimum porosity is 18%. Okay. Maximum, there is also another function called maximum, max, and I select again that column. That's just to get an idea from where to where the porosity goes. Okay, 34%. So we already have the lower and upper bound of the porosity. We just now want to find out if there is any porosity which shows up a lot of times, or if all of them appear in the same, is very uniform, okay? Or if there is one that is okay, let me put it here. Now, the next step that we're going to make, we're going to put some porosity values, okay? We're going to put here the minimum, and one will be the maximum, but I'm going to put some points in between, okay? We, ideally, like I showed you, right? You have, this curve will be continuous, okay? It will simply be continuous, right? In real life, I just have a discrete number of measurements, okay? I don't have a continuous curve. I have a discrete number of measurements. So I'm going to put here phi 1, 2 in between, 3, 4, let's maybe use 10 of them, okay? Because you're going to see now, so to calculate, let's say, this one will be the minimum, okay? This one will be the minimum, the maximum minus the minimum divided by the number of points plus 1 plus the previous. Okay? If I want to have between these two, the phi minimum and the phi maximum, if I want to have 10 numbers, okay? I want to have 1 all the way to 10. Okay? How do I calculate that? I think you can say that this spacing will be phi max minus phi minimum divided by 11, right? Is that correct? Think so? Okay. And then what I say to find this guy, I say, well, is this spacing plus this number? Okay. To find this guy, I say, well, is this spacing plus this number? Okay, and so forth. Yes. I think it's n plus 1 or n minus 1. We will see very soon, okay? But it has to be, if you have 10, right? You will have 9 sub you will if you have 10, you will have 9 subdivisions, right? Okay, so it should be here 9 actually, not 10. That is correct. Okay, so n points minus 1. Okay, so let's do that here on the right. Okay, so let's put here porosity. Okay, and we say that will be the minimum. Actually, we should calculate the spacing first. So let's calculate the spacing up here. Spacing. The spacing will be the maximum minus the minimum. I enclose them in parentheses and then divide them by 9. Okay? Now I say that's number 1, okay? So let's put here number maybe 1, and we want to have 10, okay? So the next one will be the previous plus that spacing, and I have to block the spacing, and then I drag it all the way down here. 344. You can choose any number. It has to be below, yeah, I would say it's 8. So why why 10? You can really choose any number you want, okay? The only thing, don't make it too small and don't make it as big as the number of measurements, okay? Otherwise you will have simply a trivial result, okay? Because I'm going to show you now what is the intention of this, okay? For example, if you have, the way we are going to do it, right? We say we have, for example, 1, 3, 7, 8, 9, 12, then we have maybe 4, then we have maybe 5 again, then we have 15, then we have 20, okay? We have a bunch of random numbers, okay? Now, what is the minimum here? Is 1, right? So that's the minimum, okay? What is the maximum? 20, okay? And let's say I want to take just, let's say, so I want to take 1, 5, 10 to make the distribution, okay? I have to take less numbers than the population. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? So I'm going to choose simply 1, 5, 10, 15, and 20. Okay, those are going to be my, that's what I call the bean, okay? Now, how do I count this? How do I allocate this? 11. Where do I put 11? The way I normally do, I say I have 10. 11 is between 10 and 15, right? So I say everything that is below 12.5, I'm going to assign to 10. And everything that is above 12.5, I'm going to assign to 15. Okay? So here, this 11, I will assign it to 10. Okay, so I will have 1 here. There is one occurrence of 10. Now I come to 7. 7, where does it fall? Between 5 and 10. The same thing, okay? 5 and 7, everything that is, and 10, everything that is 7.5 and below, I will assign it to 5, and everything that is 7.5 and above, I will assign it to 10. Okay? So 7, I assign it to 5, I have 1. What happens with 9? I assign it to 10. Okay, so I erase here 1, and then I say now there are 2 10s, which is not really correct, but it's the closest to 10. Okay, it's that number is closest to 10. Now, yeah, 9, 3, for example, where is it 3? Where I'm going to put it? Huh? To 5, okay, I think. Yes, to 5. So I have here 2 for 3. I count, okay? I'm counting how many 5s I have. So 8, where should I put 8? To 10, okay? Now, 5 is simply here, 5. Okay, 3. 4, also to 5, okay? Then 12, where should I assign 12? To 10, okay, so I have here 4. And then 15, I have 1 here, 20, and I have 1 here. Okay, 0. How, if I plot my distribution of these numbers, how is that going to look like? Okay, my PDF. Okay, it's going to look, here I put my number, okay, and I put 1, 5, 10, 15, and 20, okay? So it's going to have a peak, okay, around 10 and 15. It's going to have a peak here, okay? Then, sorry, 10, 5, and 10. Okay? Here it won't have anything, and here we'll have a low peak, like that. So that's the distribution, how it looks like for those numbers, okay? So if I was to say, what numbers do I use, okay? I will use 5 and 10, because they are the ones that come up the most, okay? So we are trying to do something like that with porosity. We're trying to see which porosity happens the most often, okay? So that's why we made the beans, okay? And now we have to count how many of these. So for example, this one goes in the maximum, okay? Here I should have 1. This one, 250, where does it go? Maybe here, okay? Then I should put 1. 321, where does it come? Here, I have 1 here, okay? Now 232, here probably, okay? Now this is a manual process. Remember what we say always about manual process. Computers can do it, okay? Not us, okay? It's not that we are important people, but we want to do other things, okay? So let's use a computer to count that, okay? And for that, we're going to use a function called frequency, okay? So be careful, this function is very special. Let's put here number, okay, of occurrences. Okay, how many times it happens, that value, okay? How many times do I have 182.2 and so forth, okay? I have to select the whole column to the right, okay, all of it, and be very careful. Here you have to do it extremely carefully. Now click equal to, okay, you should still have the square around, okay, equal to, and just type frequency, okay, and you can now open the function. Well, yeah, don't open the function, just leave it like that, okay? So first you see, you have to select the data array that you have, okay? You select all the data array, and I'm going to tell you why it's very special, this function. Okay, data array, comma, and then you have to put the bins. How do you want to arrange this data? How you're going to split it? So I select the porosity, these porosity numbers I have. Okay, I close parentheses, and now be careful. To apply this function doesn't give you a number. It should give you a lot of numbers. Okay, it should give you one number for each row. Okay, so to make that happen, you have to click Shift, Control Shift Enter. Okay, Control, then Shift, then Enter, and you might get some error someplace. Okay, and you see it counted automatically. Okay, the number I have 8 of this porosity, 6, 8, and so on. You got it? It's even not just one number, there's a lot of numbers at the same time. Okay, so it's like a matrix function. So a matrix function, you cannot just type enter, you have to use control shift. Okay, okay, if you have, because if you have a function, okay, that depends on, here you have just a simple number x, and you want to apply a formula that is fx. In that case, you can simply use enter. In this case, if you see, we have the input is actually a lot of cells, okay, are these cells, and I have a few cells more here. All of that is the input. This is the input, this is the input. And the output is only not one cell, but it's actually also a bunch of cells. Okay? So that's why it's important you select all of these cells, okay, and you apply Control Shift Enter, okay, and that's just to activate the matrix output, okay. It's a vector that what you output. Okay, so it's x is the inlet, and then you have a function fx that is the outlet. Okay, now let's do one more thing. Okay, we usually don't plot it like that. Okay, we want to plot is the relative number, okay, in fraction. So for that we say we're going to sum how many points there are, okay, and they should be 50. Okay, 50 points, that's correct. Okay, that's the total number of points. And now we're going to calculate actually the probability, the PDF, probability distribution function. Okay, and for that we're going to say is this number divided by the number of samples, and I have to block it. Okay, I have to press F4. So that number, if I use a porosity, the minimum has a probability of 2% of happening in the sample, okay? And the ones that have the highest are, yeah, these two, porosity of 21 and 23, and porosities of, yeah. Okay, so just once more. Here we say the sum of that column to calculate the total number of samples, okay? And then the next step is to divide each one of these numbers by the total number of samples, okay? So that's saying if I take a sample of porosity, 2% of the time, the number I take, it will be 18% porosity. 16% of the time will be 23, and so forth. Okay, now let's plot it, okay? Let's make a plot. To make these plots, we typically use a bar, okay? So I have to insert chart, and we have to use a what is called a 2D column, okay? And in 2D column, it's a bit special. Select data. We have to the name, we have to select the porosity, and the values we have to select the fraction, I think. Yeah. Sorry, the name, don't put anything on the name, okay? Just leave it empty. And the values, you select the PDF, okay? And then on the label, you select here the porosity. Okay, I'm going to move the chart. Just the PDF. We have to change this format. I want to put the tick marks, outer tick marks. Okay, and also I want to increase the size, maybe to 16 or 18. then the last thing I want to make is to make it like that. Okay, now let's, there is one more concept I want to talk about, and that's the cumulative, the CDF, cumulative distribution function, okay? Our petrophysicists made these measurements, okay? And we found that distribution, and we say, if you want to calculate, you want to use a porosity, remember, all the goal is to use it to calculate this equation, okay, this porosity. So it's saying if you're going to use any porosity for that, it should be around those numbers, okay, which are the most likely. Okay. Now I want to show also another way, another thing called cumulative distribution function. And that's useful for another, we are going to see that's what we use actually for reserves, okay? For reserves, we don't use this plot, okay? It's a bit more difficult to read. We use the CDF, okay? And I'm going to explain what it means. So on the data you calculate, okay, CDF, let's create one more column called CDF, cumulative distribution function. And initially, it will simply be the number to the left, okay, 0.02. Okay, the second one will be the previous plus the one to the left. And so forth. I can just drag that down all the way until I find one. And now let's make a plot. This one will be simpler, okay? We want to plot the CDF versus the porosity, okay? But we can plot it simply by using this scatter plot, okay? Let's use that graph. Okay, so let me change the data. The X will be the porosity, and the Y will be the CDF. Okay, and I have to adjust the axis such that it goes only from the minimum 182 only to the maximum, which was 344. You know, it's not so important that you can, you know, later put some time how to make the graph nice, okay? But I think if you know how to make the calculation, that's more important. So don't be stressed if you don't manage to make the plot. You know, the plot is a nice way to visualize the information, but it's what we want is the calculation. So that will be called the CDF. Wait. Okay, I obtained this plot that is called the CDF, and we're going to see now what does it mean. Okay, here it means I have a probability of 10%, okay, that my porosity values will be 0.02 or lower, okay? And here, for example, I have 50% that my porosity values will be 2. Yeah, maybe 2.7 and lower, okay? 50% of my samples, okay, have a porosity value equal to 2.7 or lower, okay? 80% of my samples have a porosity value equal to 0.3 or lower, okay? And we are going to see that why this is important for, this is something that we use very much for TRR, okay? And we're going to see later why. Okay, so before going to how do we use this to calculate TRR, I suggest we take a break, okay? Let's say 10 minutes break. We are back here at 1, okay? Okay, so we were saying, just to recap, that we have this problem, okay? We want to estimate this number, NPU. The problem is that we don't have a unique number for all of those. We just have a distribution, okay? And we say, well, how do we deal with that? First, we have to calculate the distribution of each parameter, okay? If I have information, I take the numbers, I make a frequency analysis, and then I calculate these two, okay? If I don't have anything, I have to start making stuff up, okay? One approach is that I say, well, you know, I have a minimum and a maximum, but I assume is all of them have the same, okay? When you gain more and more information, you're going to get more and more information about the distribution of that volume, okay? You're going to narrow it down. So I'm saying that this cumulative is important. You say here 10% of the samples will be below that porosity, 50 will have below that porosity, and so forth. So that's the way actually the reserves are plotted, okay? TRR are plotted using a CDF, okay? But the CDF is made on the opposite way, and you will see now why. We have here in the x-axis, you have the TRR, okay, where you have a maximum and you have a minimum. But the curve is plotted like this, okay? Actually, the plot is going like that. Okay, and here you have 1 and here you have 0. So if you take a fraction here, for example, let's say 10%, okay? That number here means this number typically we call it P10, and you will see that number reported many places in when you read a kind of a reserve estimation report. Okay, that means there are 10%. There is a 10% probability that reserves will be equal or higher than P10, that number P10. Okay, so that's something very risky. If you make your planning based on that number, you only have a very small probability that your reserves will have that number or higher. Okay, then you have some other number that is used is 50. Okay, and again you have here P50. Okay, and here you have there is a 50% probability that the reserves will be equal or higher than P50. Okay, and then finally you have P90. That's very conservative, and that's what many countries are using. Okay, P90, and you say there is a 90% probability that reserves are equal or higher than P90. Okay, so these are the three numbers. Usually you have a distribution. Okay, and the PDF of the TRR are also, we are going to see now how to calculate, but it's also going to look something like that. Okay, but actually we don't use the PDF, we use the cumulative. Okay, because we want to be sure that we have at least that number or higher, at least that number or higher. Okay, that's the way the industry works. P90 is a number, the number that you most typically use. You want to have a 90% certainty, but some people, you can really use, some people like to use 66, any number between 90 or 95. Some people use 95. They want to be really, really sure, all the way to 66%. Okay, that depends on the company, that depends on the, what happened here. Okay, 55 to 66. Okay, now how do we compute this? Okay, we know, so you got some intuition, right? The intuition is that if you have here a process, okay, that is reserve estimation, okay, that is that formula, right? NPU phi VR 1 minus SW net to gross FRU divided by BO, right? And you have different inputs, okay? Phi, you have saturation, you have volume of the rock, you have net to gross, and you have FRU, and you have BO, okay? All of these inputs are going to have their own distribution, okay? Their own PDF. Okay, maybe BO is like that. Maybe this guy is like that. Maybe this guy is something like this. Okay, this guy might be, I don't know, something like that. This guy might be like this, and this guy might also be, we found it just now, right? Looks something like that. Okay, so we have a suspicion, right, that if all of them have that distribution, probably this guy, the NPU, will also have a distribution like that. And it's actually going to show like what I showed you before. It's going to look like that. Okay? But now how do we calculate this thing? How do we calculate that? Based on all of that input. Okay? So there were actually not so long ago, okay, on the 50s, there were two clever guys working in this development of the atomic bomb, okay, from Los Alamos laboratory, okay, that came with a method that's what we use in the petroleum industry to calculate reserves. These two guys, Metropolis and Ulam, and they are the ones that have the credit of inventing this method that is called Monte Carlo, exactly to calculate this thing. Okay, Monte Carlo, they say one of them, I think was Ulam, liked to go to the casino to do betting, so he was trying to use the method for that, and that's why they call Monte Carlo. The idea is very simple. They say the first step is to take first to assume a random number. So that's the first step, assume a random number for each parameter. Okay? Assume a random number. And of course, the random number has to be inside the distribution. Okay? Inside the distribution. Okay? The second step is to perform the calculation, what they call the simulation. You are going to assume a random number here, random, inside the distribution, you calculate that and you compute NPU. Compute NPU. Okay? Third step, repeat for many times. Okay? Many times. 10,000, 1,000, as many as you can calculate. Okay? You repeat step 1, 2, and you're going to get many NPUs. Okay? You're going to get, here we call it Monte Carlo iteration. Okay? Monte Carlo iteration. 1, 2, 3, 4. And you're going to have a different number of NPU. Okay? NPU 1, NPU 2, NPU 3, and so forth. Maybe 1,000, 10,000, whatever you choose. Okay? And then at the end, you're going to apply the fourth step is to apply a frequency analysis on the output, okay? On the output values. That's the last and final step. I generate a lot of output and then I analyze the output, and then finally with that I'm going to get my distribution. Okay? So that's what we're going to do now with to calculate reserves. But basically is you take a random number, you introduce it here, calculate NPU, repeat another random number, calculate an NPU, and so forth. This is known as a sampling method, okay? Monte Carlo is a sampling method. And the idea is to find a representative sample of the whole population. Okay? We know if we change these numbers here, we're going to we can have infinite combinations. Okay? Here you have maybe 10,000 values, 10,000, 10,000, that gives you too much, okay? 10,000, if you have 10,000 on each point, to the power of how many you have here? 1, 2, 3, 4, 5, 6, okay? To the power of 6. You'll have to run, you will be your whole life making calculation. So Monte Carlo saying, well, you don't have to make so much, okay? Just make a few iterations, okay? And then you find a representative sample of the whole population, okay? It's like if you have a function, okay? A function that depends on x and y, okay? You have two axes, x and y, okay? And you want to see how that function will look like. You want to see how the function looks like. So you make a grid here, okay? And you start evaluating random points, okay? To try to see how that function will look like. Maybe it will look something like that, I don't know. Okay? It has some behavior, something like that. Okay? So you're taking random points, but you have to have enough such that you find exactly how the function looks like. Okay, and that Monte Carlo is taking this sampling in a random way. Okay, there are some other methods, sampling methods, that are more structured, that I just make some sort of a grid. Okay, this is called orthogonal sampling. Okay, I just make exactly a very well organized grid, and then I just make a sample in one of these points, and then I cover. Okay, so that's the whole idea of the method. And the way we make one question is how to generate the random values, okay, of the input. That also is a bit tricky, okay. They recommended that you should use the CDF, okay, of the variable. Remember the PDF, okay, let's say of the variable, maybe look something like that. The PDF will look something like this, okay, from 0 to 1. So they say it's better to do it in CDF. Why? Because here the number is simply between 0 and 1, okay? 0 and 1, you choose a random number, then you come, and then you find your variable. Okay, another random number between 0 and 1, 0.9, and you find your new random variable. So you're going to do exactly that, to make the sampling or generating the random value using the CDF, okay? And to make our life easy, okay, we're going to use for our input only a kind of uniform distribution. Okay, that means that every variable, porosity, etc., will have simply a uniform distribution like that, phi minimum, phi maximum, and PDF. And the CDF, therefore, is going to look like this, okay? Phi minimum and phi maximum. Therefore, the phi will be the phi minimum plus a random number between 0 and 1, okay? This is between 0 and 1, times phi minimum minus phi maximum minus phi minimum. Okay? So that's the equation we're going to use now in our Excel expression. Okay, assuming completely uniform, we're taking a number here and finding a number there. Okay? There are other more complicated functions like a triangle. They are like normal distribution. To keep our life simple, let's make it uniform. So let's now go to the exercise, okay? The last exercise we're going to do today. And that's exercise 7, probabilistic estimation of reserves, Monte Carlo. Okay, all of you have this file? Yes? Okay, so you see here Monte Carlo iteration. We want to have here, let's say 1,000. Okay, let's start with 1,000. So let's put 1, 2, and then maybe I can drag it all the way to 1,000. Want to make 1,000 samples, and I'm not sure if that's enough, but let's make to start with just 1,000 iterations. Let's change, I don't know why these numbers are like that. Let's change that to scientific. Scientific. Okay, so now let's do exactly what these guys suggested. Okay, I take a random number between these two, okay, between these two, a random, and then I calculate NPU. Okay, let's do something. You know, I think just to make our life easy. Okay, if you punch Alt F11, okay, you're going to enter into the VBA part. Okay, then go to the left and double click on module, and that's the place where I save all my functions, okay, for that sheet. Okay, I save all function, everything is like a repository where I have all my functions. And we're going to see very briefly how to make a function, how you can make your own function. Okay, I think that will be useful for you. To make a function, first I declare there is a function. I say function. Okay. Then I put the name of the function. The function will be NPU, right? Ultimate cumulative production, or total recoverable reserves. NPU. Okay, let me put it lower. Okay, now I open parentheses and I say what is the input of that function. Okay, the input was VR, right? Rock volume, comma. I separate the input with commas. VR, next one was porosity, let's put phi, comma, water saturation, SW, comma, net to gross, NTG, big N, I put big N, TG, comma, what else? Recovery factor, FR, comma, BO, and I close parentheses. Okay? My function, if the name is NPU, depends on rock volume, porosity, saturation, net to gross, recovery factor, and BO. Now if I click enter, at the end of that line, it's going to automatically, Excel is clever, so it says you're trying to declare a function, okay? So it makes the end function automatically. So what is the equation for NPU? So I simply write NPU is equal to VR times phi, and I have to use exactly the same way it is written at the top, okay? Times, open parenthesis, 1 minus the water saturation, close parenthesis, times Net to gross times FR divided by BO. Okay? And then if I click outside, let's say I click at the end of any function, it should, if there were no problem, it's going to expand. Okay? Excel puts it such that it's easy to read, the space between them. You have to be careful that you're using exactly the same name, okay? Up and down, they have to have exactly the same name. Okay? You can do it without this, okay? But I just thought it's nice if you learn how to do your own functions, okay? So you can, if you want to keep using Excel in the future, you can do it. Okay, let's go back to our Excel sheet. We have to generate a random number here. How do we do it? We already explained before, right? Minimum plus a random times a maximum minus the minimum. Okay? So let's do that. So this will be, rock volume, will be the minimum plus a random number. For Excel to generate a random number, I use the function RAND, rand, okay? And you see the description returns a random number greater than or equal to 0 and less than 1, evenly distributed. Okay? Sorry, here we forgot we have to block B5, okay? Because we have to block it, otherwise it will change. Random, I have to open and close parentheses. That function doesn't take any input, but it's still a function, so you have to open and close parentheses. Times phi maximum, this guy, block it, minus the minimum, unblock it, and close parentheses. Now don't press enter yet. Okay, I'm going to show you a trick. If you do it like that, okay, you'll have to do it for every of the other parameters, okay? But if you see, if we drag to the right, okay, if we drag this cell to the right, it will be very helpful if these ones would also move to the right, right? So the way to do that, but when I drag it down, I want it to be the same cell, to keep it in the same cell. To do that, I have to use a different type of blocking, okay? This dollar is blocking on the column. It doesn't allow it to move to right and to the left, the letter, okay? But the number is blocking it on this direction, okay? It doesn't allow it to go up and down. So if we remove the block on the letter, it will be able to go to the right or to the left, okay? So if we remove the dollar before the B, then it will be able to go to the right or to the left, but it won't be able to go up and down. And that's exactly what we want. Okay? So just remove before the letter the dollar sign. Okay? And click enter. And you see it found a random number between 2 and 2.5. And then I just drag it all the way to the right. And it should work. Should work fine. Don't put it in the last one will be the admission. Yeah, you're getting a different random number. Remember, the random number you have will be different. Okay? Don't worry if you don't get the same result. The random number generator is different than mine. Okay? We have different computers. Okay, so now let's use that function, right? We have all of the random input that Metropolis and Ulam said, okay, in their method. So now we say NPU, and you see it came up now. NPU has a function. So I select it, then I say that is using the rock volume. I don't block anything. I want it to drag it down and that it will be applied for the rest. Porosity, this guy here. Saturation, this guy here. Sorry, saturation is this guy here, sorry. Net to gross is this guy here. Recovery factor is this guy here. And BO is here. Be careful, just be careful with the input, it's not in the same order, okay? BR, porosity, SW is E, T is NTG, recovery factor is 0.64, and BO it's 1.3. Okay, and that tells me that the NPU is, if you see here in my case, is 10 million barrels, okay? You are going to have a different number because your computer has a different random generator. What you have to check is that the numbers here are between these two, always. That's what you have to check. If they are between them, that's your calculation is probably right, okay? So here I have 13 million, yeah, 30 million. So that was the first step, right, from our Monte Carlo method. The first step, assume a random number for each parameter. The second step, compute NPU. What is the third step? Repeat the same thing 1,000 times, 10,000 times, okay? To repeat, in our case in Excel, we take this line and we just simply double click. Here I'm making all iterations. Excel is doing them by itself, okay? And I want to check here that I is always taking the same two numbers. Oh yeah, that's correct. Yeah, so we should put 1 minus that, okay? So that's an error. So we should put here 1 minus saturation, okay? Very good that you noticed. Okay, what is the next step? The next step is frequency analysis on NPU. Okay, that's the next step I have to take. Make a frequency analysis on the output. For that I have to copy this column. You know, here you have to be careful, okay? Every time I make a change, okay, you see that the random numbers are changing, okay? Every time I click every place is changing the random number. So that takes a lot of memory from the computer. So I suggest when we do the frequency analysis to keep this file closed, okay? So let's just select this column, okay? Copy, and then we open an empty Excel file and we paste it there, okay? We say NPU and we paste only the values, okay? Paste special, copy, and paste special only the values, okay? And I close this file. I don't need it anymore because it will keep changing the random numbers, okay? And that's making my computer heavy, difficult to use. So I simply close this file, okay? And then I'm going to use these numbers. SPU, that's in standard barrels, and these numbers, they should be in scientific. Scientific, okay? To make the frequency analysis, what is the next step? Find the maximum and the minimum, right? Minimum and maximum. That will be in standard barrels. Okay, the minimum. The same thing here, we're doing exactly the same we have done before. And the maximum. So the minimum is 30 millions and the maximum is 128 million. Okay, you see it's a big spread between the numbers. It can be 30 million, a very small pocket of oil, but can be 120. It's becoming like a small to medium sized field. Now I calculate, how did we call it? Is the segment, okay? How did we call it before? We call it the spacing, okay? So let's say spacing will be, and let's use now, let's use not 10, but let's use 20, okay? Let's use a bit more numbers. So let's say maximum minus the minimum, and that I divide by 19, okay, to have exactly 20 points. Then I create my beans, okay? Then that will be the minimum, and this will be the minimum plus the spacing, and I block the spacing, and then I pull it down, and it should go all the way to 128, okay? 128. Then I say here numbers, 1, 2, 3. I'm repeating exactly what I have done before, what we have done before. Okay, 20 numbers. Now, frequency function, okay? I put here number of occurrences. Okay, I select equal to frequency of this guy, comma, the bean. Okay, in my case it's not comma, this Norwegian keyboard, so it's likes to use semicolon, and then I use Control Shift Enter. Okay, next step, calculate the sum. How many points do I have? Exactly the same that we have done before. Now the frequency, that will be this number divided by the number of samples. Okay. And finally, we can calculate the CDF. Okay. And here we have to be careful. Okay. In the previous case, in the porosity, we were summing from top to bottom. Okay. We obtained one here. But if you see what we discussed before, okay, we have the CDF like that, but for reserves, we like to have it in this way. Okay? So in that case, we're going to sum from bottom up. Okay? So this one will be simply this one, and this one will be the one from before plus the one to the left. I pull it up, and I have one, and then I just make the plot, okay? Just to see what we have. Okay, here we have already our expression. So let me put that in a new view as a CDF. This is not. Here it should be the pin, so it should be G. NPU. Okay, so we got this, but we have now to plot from the minimum to the maximum, 30, 128. Okay, and that's how the cumulative distribution looks like. And let's copy also the data so you have it. That I don't need anymore. Okay, so that's how it looks like. You see, it looks very normal. A normal distribution, a standard distribution. And you have, has a homework, you have to do it yourselves, but you should get similar numbers, okay? You won't get exactly the same because your random numbers are different, but you should get similar numbers. Okay, so that's a PDF. We don't use it much for reserves, okay? It's just nice to have. But we really like is this one. That's the one that we are using every time. Okay, and we are going to take one screenshot of this guy. Okay, now let's see on the results, okay? What are the three numbers we have to report, okay? If you remember before. P10, yes, how much is P10? We go here, and these numbers, which you should obtain similar numbers that I'm getting, okay? Not exactly the same, but very similar. 10%, then I knock it down. How much is that? Like this is 100, so it will be like 95, okay? So P10 is 95 million standard barrels, okay? That means there is 10% chance that my reserves are 95 barrels or above. This is very risky. It's only 10% chance, okay? If there is a chance, but there is only 10%. P50, okay? P50 is 70 e to the 6, okay? There are 50% probability that my reserves will have at least 70 million barrels or bigger. And P90, how much is that? Like 60, this is 60, that's 55, 52 point. P90 is 52.52 million. Okay? So those are the three numbers. If you see on the Hebron PDO, they should have some distribution like that someplace on the reserve estimation. That's the forecast. Let's see if we find it. Let's see which page was it. reserve estimation, reservoir overview, reserve estimates, 5.1. So let's find that page, 5.1. I'm going to give you this document tomorrow, okay? So you can have it as a reference and you can see what kind of activities are made in when you develop the field. Where was it? 5.1, reserve estimates. Okay, they call it upside, okay, best estimate, and downside, okay, volumes. That's the initial volume in place. That means that's N, and instead of calling P10, P90, P50, they call it best estimate, upside, and downside. Okay, that's P90, that's P50, and that's P10. Okay, so let's call that, but they have to do it for different regions because they have a bunch of other regions. Okay, and they have to do it also, they have a gas cap, so they do it for the gas. But we have obtained something similar. That's, let's call it here, from Hebron PDO. Okay, and let's see if they have the distribution. Yeah, they don't, I don't think they give the distribution. Okay, they don't give it. They just give the three values, P90, P50, and P10. Okay, they call it, let's write it here. Okay, upside, that is something similar to P10. Be aware they might be using a different number. Okay, they might be using 12, might be using slightly different. P50, and that is P90. Okay, so I think okay, so let's make a quick summary. Okay, today we talked about networks. So what happens when wells are actually different? Okay, in the example we have done yesterday, we're assuming that all wells are identical. In reality, wells are going to be different, and we have to be able to calculate the performance of the field in that case. Okay, so I explained how to do it graphically, and that came in an exam last year. Okay, or we also said how to solve it with Excel. Okay, how do you solve it numerically? And in that way, you have to run that calculation, okay, every time for every year. Okay, you have to calculate with every year the choke or the rate, and then you go to the next year. We don't do an exercise, it's a bit too heavy to do it in class. Okay, then I made you aware that this network solving philosophy can also be used to solve downhole systems. Okay, first injection, but also downhole. And why do we have downhole systems? For all kind of reasons. Okay, then we solved that exercise in Excel. Then we went to this topic called reserve estimation. Okay, that's something we have to do along the field development process from DG0 to DG3. Initially, we have very little information, and after we're going gaining more and more and more. Okay, we talked about how the values are gathered. How do you gather the volumes? How do you gather the properties of the fluid? We have coring and logging. And at the end, we use, actually maybe here I should put BO, right? We use a simple equation to reflect just how uncertain the input can be, okay? And we look at data measured from porosity from the field. We had 100 measurements, 50 measurements of porosity in the field from cores, okay? And we try to show how that distribution looked like. And from our sample, that's the distribution we obtain using a frequency analysis. That means that 60% of the samples have a porosity of 24%, okay? 12% of our samples have a porosity of 22%. Again, so forth. Then we came and said, how, if we have uncertainty in all the input, how do we reflect that uncertainty in the output? Okay, and there were two very clever guys that developed this method. That was in 49, in the 50s, in connection with the development of the atomic bomb. Okay, they call it Monte Carlo, and basically it's making a random sampling in the input. Okay, where do we have the input? The steps are, you assume a random number at the input, has to be inside the distribution, run the simulation, compute the value, and then repeat many times. And the number of times is until the distribution doesn't change much. Okay? You do it for 500, 1,000, 6,000 until the distribution you obtain doesn't change much. And we show that the distribution you get for that formation looks like that, and from there we can get the three numbers that the authorities need or we need to make our calculation. Okay? Typically for our, so what you will use for the calculation we have done yesterday, you will use 50. Okay? You don't use the most positive or the most negative, but you choose the one in the center, P50. So that's how you calculate your profiles. So P50 is usually used for production forecasting. Okay? Profile forecasting. Okay, so that's all I had to say for today. I suggest you work a bit more on, just continuing such that you reach the same point, okay? Like I say, the plots are not important. The important is that you understand what the plot is saying and you can extract data from it, okay? But you have to make the calculation. You have to generate the numbers. And tomorrow, we're going to talk about, not for all cases, we can use this approach, okay? This is very heavy. And in our case, this function runs like that, okay? We just double click and it calculates all the numbers. In reality, this process takes a lot of time, like calculating the profile, okay? We were yesterday like half an hour. If every iteration takes half an hour, you cannot make 1,000 iterations. You cannot make 1,000,000 iterations, okay? In a simple way. So for that sense, we use another method that we're going to discuss tomorrow, that is called probability trees. That is very much used in the oil industry, okay? When the simulation takes a long time, okay? That is typical when we calculate production profiles, okay? Or, for example, when we estimate cost estimation, or when we make NPV calculations. Simply, Monte Carlo is just non-practical. It will take forever. You will be waiting for a year for the results, okay? Monte Carlo is impractical. That means too long running times. Therefore, we use probability trees. Okay, and that's what we will discuss next class. Okay, probability trees, and we are going to go on the offshore part. How do you select the offshore structure? That's also a big part of the field development. Okay, so we close our session. Thank you for coming. See you tomorrow.